In this video, we're going to continue to analyze a titration involving a strong acid and a weak base. So for this titration, we're going to be having our strong acid in our burette, and we're going to be adding the acid into a flask containing a solution of a weak base. A typical titration curve for this type of titration would look like this. You start out very basic since we just have a weak base in water. As we add the acid, the pH decreases rapidly at first, then slowly, until we get to the equivalence point, and we get a dramatic drop in pH. Then it begins to level off again. The equivalence point for this type of titration is always going to end up being below 7.0. So for calculating the pH for a strong acid weak base titration, we need to be able to calculate the pH at the following points. Before we add any acid, so before we start the titration, after we've started to add acid, but before we reach the equivalence point, calculate the pH at the equivalence point, and calculate the pH after the equivalence point. Each of these points along our titration curve requires a different method for calculating the pH. So we're going to talk about each one of these individually in a separate video. In this video, we're going to show you how to calculate the pH after we've started the titration, but before we've reached the equivalence point. So again, on our titration curve, we've started the titration, so we're somewhere in here, but we haven't reached the equivalence point. So our titration, what we're showing you how to calculate the pH for is a region somewhere in this, along the titration curve right in here. So what steps do we need to follow in order to calculate the pH of our solution before we've reached the equivalence point? Well, the first thing we want to do is always check to see if the titration is before, at, or beyond the equivalence point. The question may not tell you. Obviously, in this video, we're going to show you how to calculate the pH before the equivalence point, but it's always good to check to see where you're at. Second, we need to be able to write a chemical equation for the weak base solution after we've begun to add our strong acid. And then, as we'll see, we set up a buffer solution at this point in the titration. So we use the Henderson Hasselbalch equation to calculate the pH. So in this video, we're going to be showing you an example titration under these conditions. So take a second and write these down so you can follow along with the video. We're going to have 30 milliliters of 0.200 molar ammonia in our flask. Here's the KB. And we're going to titrate that. We're going to add a certain volume of 0.300 molar HCl. So write those conditions down. Specifically, the problem we want to solve in this video is we want to calculate the pH of our solution after we've added 15 milliliters of our 0.300 molar HCl. Now, if you would, why don't you pause the video and follow the steps we just covered and see if you can calculate the pH correctly. Give it a try, whether you get it right or wrong, and then follow along with the steps that I go through. So pause the video and give it a try. Okay, so we're adding 15 milliliters of our HCl. Let's check to be sure that the 15 milliliters doesn't put us at or beyond the equivalence point. So let's see where we're at there in our titration curve. What we need to do is we need to take the moles of our ammonia that we were starting with and compare that to the moles of HCl that we've added. And again, for this, we're going to be representing HCl as H3O plus or hydronium because this is kind of a shorthand way for writing any strong acid. Since they dissociate completely, HCl really doesn't exist in solution. It exists as hydronium. So let's take our moles of ammonia that we started with. Let's calculate that. Our flask, our problem told us that we had 0.003 liters or 30 milliliters of ammonia, and we're also given the molarity of our ammonia. So we can use these two to figure out how many moles of ammonia we started with in our flask, and you can see that's 0.006 moles. Now, how many moles of hydronium, or HCl, have we added? Well, our question told us that we added 15 milliliters, so we converted that to liters, and we multiply it times the molarity. Our liters cancel, and our molarity of the HCl was given in the problem. And so we've added, up to this point, after we've added 15 mils, we've added 0.0045 moles of hydronium. So let's compare these and see what it tells us. At this point, we have added less moles of acid than we have moles of base. So we have not neutralized all of the base. That tells us, since our moles of ammonia is greater than the moles of acid added, that we are before the equivalence point. Remember, when these two numbers are equal, by definition, we have reached the equivalence point. We've neutralized all the acid. When our moles of hydronium is bigger than the moles of weak acid that we started with, then we're beyond the equivalence point. So at this point, we should be able to recognize that we are before the equivalence point, and so we want to apply the appropriate strategy for solving that. The first thing we want to do is write a balanced chemical equation showing the reaction between ammonium and our HCl, or H3O+. So after the addition of HCl, the HCl and the ammonia react to form our conjugate acid and conjugate base. So the equation should look something like this. Again, we're representing HCl as hydronium for simplicity's sake. So our hydronium plus our ammonia, that's what we have in our solution so far, are going to react, and they're going to neutralize each other, and we're going to form water and our ammonium ion. So this would be our balanced chemical equation. Take a look at it and be sure you convince yourself that this is correct. So another thing that's very important is that you appreciate the stoichiometry here. For every 1 mole of acid that we add, 1 mole of ammonia is neutralized and 1 mole of ammonium is formed. So for every 1 mole of acid that we have, we're going to form 1 mole of ammonium ion, and we're going to lose 1 mole of ammonia. That's very important, so take a minute and write that down. So step 3, since both at this point in the titration, we still have some ammonia present, and we have formed some ammonium ions. So what we have here is a solution with a weak acid and a weak base and its conjugate acid. Anytime you have a solution that contains a base and its conjugate acid, or vice versa, you have a buffer solution. So the easiest way to solve a pH involving a buffer solution is to use our Henderson Hasselbalch equation. So again, at this point in the titration, we have not neutralized all the ammonia, and we have formed some number of moles of ammonium, so we have a buffer solution. So let's take a look at how to solve this using our Henderson Hasselbalch equation. Here's the equation. Our ratio here, base, concentration of base over acid. Our acid is going to be the concentration of the ammonium that has formed up to this point. Our base concentration is the concentration of the ammonia that's remaining, not initial, but remaining. And then, of course, the pKa, we need our Ka value. Not the Kb that we're given. We're going to need a Ka in order to use the Henderson-Hasselbalch equation. So let's take a minute, and we need to get this, and then we need to get our Ka value in order to solve. So let's do this one first and figure out how to get the concentration of ammonium formed. So let's calculate the moles of ammonium formed. Remember the stoichiometry that we just talked about. For each mole of acid that we added, we've added 15 milliliters of acid to this point. For each mole of acid, 1 mole of ammonia is neutralized and 1 mole of ammonium is formed. Therefore, the moles of ammonium formed is equal to the moles of acid that we've added up to this point. This is very important to appreciate the stoichiometry in order to be proficient at titration problems. So let's do this calculation. To this point, we added 15 milliliters of acid. Let's convert that to liters. And we know the molarity of our HCl solution. So we multiply by the molarity, my liters cancel, and I end up with 0.0045 moles of acid added. We actually already calculated that. And that's the same as the moles of ammonium produced, not added, but the moles of ammonium that have formed. Because again, those are stoichiometrically equivalent. So to this point, we've produced 0.00450 moles of ammonium. Next, let's calculate the moles of ammonia remaining. Remember, we've neutralized some of it. And again, let's look back at our stoichiometry. For each mole of acid that we titrate in, 1 mole of ammonia is neutralized, and that's important. And then, as we said, 1 mole of ammonium is formed. Therefore, the moles of ammonia that are remaining in our flask is equal to the moles of ammonia initial minus the moles of acid added. So we subtract those two in order to figure out how many moles of ammonia are remaining. So our calculation would look something like this. Here's the moles of ammonia initial, and I just put that here. We've already calculated that in step 1 when we were looking to see if we were before the equivalence point. So look back at that calculation. We've already taken the initial volume times the molarity to get our initial moles. And then we just calculated that we've added 0.0045 moles of hydronium in the previous step. We just showed you that. So we subtract those two because for every mole of acid that we add, we're losing or neutralizing a mole of ammonia. So how many moles of ammonia do we have remaining? We just subtract those and get 0.00150 moles of ammonia remaining. Now, to use the Henderson Hasselbalch equation, we want to convert these into concentrations. So in order to convert our moles of ammonia and ammonium into concentrations, we have to divide moles by the liters. So let's figure out the total volume at this point. Remember, we started out, our flask of ammonia was 30 mils. That was given in our problem. Our problem also said that we added 15 mils of acid, so our total volume at this point is 45 milliliters, which we can convert into liters very easily. So we take the moles of ammonia, which we calculated, divide by the total volume at this point to get the concentration of ammonia, take the moles of ammonium formed by the total volume, and that gives us the concentration of ammonium. Again, we have to have these in order to solve our Henderson-Hasselbalch equation. The third thing we said we had to do to solve the Henderson-Hasselbalch is to get our Ka value. But since ammonia is a base, we were given a Kb value. But we can convert Ka to Kb very readily. Ka is equal to Kw divided by Kb. So we just take our Kw divided by the Kb, and we get our Ka value. Now we have everything that we need to do in order to solve for the Henderson-Hasselbalch equation and get our pH. So our Henderson-Hasselbalch equation, again, is as written. Up here, we're going to plug in the concentration of our base, ammonia. Down here, the concentration of our acid, ammonium. And then we're going to take the pKa, so the negative log of Ka. So we plug that in there. Here's our Ka, concentration of ammonia and ammonium that we solved previously. We divide those, take the log, and then we take the negative log of the Ka, add those together, and we get a pH of 8.78. So in order to solve for the pH before we reach the equivalence point, but after we started the titration, we need to follow these steps, which include using the Henderson-Hasselbalch equation to get our pH. So go back and review those steps. Be sure you're comfortable and familiar with them so that you can solve any problem of this type.